Okay, welcome to discrete math class. And I have shared some information related to chapter 4 and 5 before I come to the class. I have uploaded a file which was graded on some problems in chapter 4 and 5. I think that can be found in here. Some of you already solved some problems in chapter 4 and 5, and it was finalized, so I did graded them some before you submit your PBL report. This is number 1 in chapter 4, and he found the correct algorithm, but I asked you to add the image of the output that he got, and title should be added, and mathematical symbols should be written mathematically as italic like this, and it also need the output, not only the code, to make sure it works okay, and also we can make change to improve the given algorithms, and also Aisu and Jeonjongmun solved the problems in chapter 5 like this, and the number, changing the decimal number from binary to hexadecimal, and solved. So you must work hard to solve these problems to understand before you come to the class. 7, Euclidean algorithms. Yes, sir. So if you read this, it will make much easier to you to understand the content in chapter 5. And also, Omjagyun, and I gave most of the answer that you made. And Man Woo-hum, he solved the problem 14 in page 248, which was already solved and finalized, and which was graded. So you should follow the format that we have fixed. Your online attendance was noticed, and Mr. Odong-chan added the code he missed. He said he uploaded the file, but I couldn't find it, so I asked Mr. O to upload it, and he did so. And sometimes I'm sharing you some interesting articles. This is about too much of teaching and but poverty of doing. That means 학습의 빈공. But because of those worry, and we are not following the traditional way of learning and teaching, and that's what we are doing, is active learning and problem-based learning as we have done. Anyway, and also when I added these articles, and some of you may leave a kind of comment on these. Also, you can share, you can use that article information with your comment in your PBL report. That will be counted. Okay? Not just skipping it. If you agree, then you say something. If you do not agree, then you can say something so we can talk about. That also a part of learning experience from this discrete math class. And team, you have made the team. Okay, we have to fix. So now, we will have about 8 or 9 teams of 5 members each before this class ends. So for those who couldn't find a team, that the team leader want himself or her will leave, so I can help them to form an extra team for them. Next, yes. So Mr. 전종문 formed a team, which is team 2, with 양진욱, 이휘소, 조영은, and 주신이. Okay. And 조영은 양? 조영은 양이 행렬에 대해서 고등학교 때 전혀 배운 적이 없는 거예요. 이건 별로 어려운 건 행렬 배우는 시간이 아니니까 그냥 행렬 곱이 어떻게 되는 건지 알겠죠? 이 기역자 같이 이제 로우하고 컬럼을 각각 곱해서 더하는 거. 그 이해가 됐죠? 그럼 질문하고 이렇게 답변을 얻었잖아. 그래서 이해가 됐잖아요. 그러면 질문을 이렇게 했더니 답변을 이렇게 얻었다. 그래서 그걸 Q&A에 정리해 놓을 수 있죠. 그렇게 하고 그거를 PBL 보고서에 포함을 시키면 그게 점수가 되는 거예요. 오케이? You can add those questions and answers like others. 그러니까 뉴스라든지 무슨 아티클에 대해서도 그거에 대해서 자기가 의견을 내고 또 토론을 하고 정리가 되면 이렇게 그것을 한 페이지로 마무리해서 집어넣으면 그게 여러분 점수가 되는 거예요. 김태희 양 같으면 오히려 그런 거로 점수를 따지 않으면 이게 문제풀이하는 건 또는 코드 짜는 건 소프트웨어 학생이라든지 또는 수학 학생들보다 불리할 테니까 뭔가 다른 데서 뭐 활로를 찾아야 되지 않겠어요? 그러니까 I will expect such an activities. So you should answer all of the comment, the note that I made. You should respond on those, particularly more than others, if you want to pass. Okay? Mohammed. Make many questions. He said. It is very welcome. 이휘소. 굿. 이휘속은 어디 있어요? 저기 책을 읽으면서 일부러 사실은 틀린 것도 있고 틀린 것도 안 고쳐주고 넘어가는 경우도 있어요. 왜냐하면 크리티컬 리딩. 그러니까 실제로 이렇게 알고 읽을 수 있죠. 그냥 눈으로 겉으로만 읽지 않죠. 자꾸 지적을 해요. 그거 다 점수를 줄게. 물론 이전에 찾은 것도 있지만 내가 못 찾은 것도 자네가 찾는 것 같으니까 that's a good habit. Critical reading is a good habit. inquiry. Okay, good. 이휘속은 그리고 내가 픽스 할게. 그러니까 안 고쳐 있으면 한번 들러서 내 방에 들러서 내가 내 서버에서 바로 고치니까 그냥 만약 안 고쳐지고 있으면 나중에 모아서 그러니까 PBL 보고서에 이걸 다 올려놔요. 그럼 내가 한꺼번에 모아갖고 한꺼번에 다 고칠 테니까 안 고쳐지면 들러서 나랑 같이 고치자고. 그렇게 하면 다음 사람들이 도움이 될 테니까. 오동찬 군, 서명원 군, 오동찬 군 이거에 대해서 16번에 대해서 답을 했어요. 확인해서 그 중간 과정이 스킵을 좀 한 것 같은데 거기에 설명을 좀 더 달도록 하세요. You guys and finance. You guys and Chinkis. You did give a clear answer for problem number 4 in chapter 4. And also, 강병훈 and 김주영, did give a good solutions. And 정호진, 서명원 군, 엄자균, 는 아직 안 왔고, okay. I found there are some gap in your solutions, so try to add those extra explanation, so others can read your solution more clearly, okay? Okay, 신혜수, 정종문 solved it well. Yes, 김희성 군, 그래요. 그러니까 그냥 코드만 덜렁 주지 말고 코드를 짰으면 실제로 돌리면 스크린 나오죠. 실행한 이미지 있죠. 그런 거야? 오케이, then 그 설명한 거고. 그러니까 그거 다 해보니까 어떻게 하면 쉽냐면 실제로 실행하면 화면 뜨잖아. 화면에 뜬 거를 그냥 스크린 얼터 프린트 스크린 하면은 그 화면만 뜨거든. 그걸 그냥 쉽게 카톡에다 갖다 놓으면은 컨트롤 V 하면은 그냥 바로 그 이미지로 저장되잖아. 다른 소프트웨어 그림판 같은 거 안 써도 그걸 그냥 자기 짠 그 코드에다가 아래다 달면은 실제로 실행됐다는 걸 확인할 수 있으니까 다른 사람이 그걸 다시 자기가 확인해보고 그러지 않아도 되잖아. 그러면 그 다음에는 그걸 좀 더 고치는 것만 생각하면 되니까 그런 의도였어요. 설명을 그런 의도가 아니라는 걸 설명을 달아서 마무리 짓도록 하세요. 그래서 PBL 보고서요. 김희성 군, 코드를 이미 C로 새로 짰는데 그럴 필요 없이 이미 책에 그 파이썬 코드를 준 게 있으니까 그냥 그거를 활용해도 돼요. 어차피 새로 짜지 말란 소리예요. 김희성은 모하메드, 칭키스, 전종우, 오동찬, 강병호가 굿. Yeah. Then okay. I think that's what the comment that I gave you for about a week so far. Let's see. Here. 야, 이제 김이야, 김태희야. 어쨌든 야, 어저께도 스포츠 과학 학생들 때문에 회의가 있었는데 그래요. You have to show what you can do. 오케이, good, 좋아요. Next. Any questions before we start chapter 5? 이거를 전체를 보기 그냥 이렇게 하자. Okay. Then we will start chapter 5. The number theory. This is just a simple introduction. The number theory is a whole 1-year course for math major students, but this is just 2-hour lectures for just introduce what is the number theory. You already studied, and I gave you the lecture, online lectures, and the laboratory, the content. So you did study, and you solved the problems that you already saw. But so I can go it briefly. So we will finish up our class much earlier than it is scheduled. Okay, number theory is the part of mathematics to study the set of integers and their properties. In this chapter, we will study some concept of number theory, which has been used heavily in computer science. In that process, we will use the proof method that we have learned in chapter 2. These are the lectures and lecture note and laboratory and the lectures that you studied. Okay, you know, if D divides N, then we write it as D divides N like this, and we say D is a divisor of N, and Q is a quotient when N is written as a DQ. So D divides N, then D is a divisor. And this Q is a quotient. So 3 divides 21, so 3 is a divisor of 21, and 7 is a quotient. If D divides M and D divides N, then D divides M plus N. Easy, because from this we know there is a D that makes N is equal to DA, and for here, DB, and for here D divides N means there exists an integer A that makes N is equal to DA. So if we add N plus M, then DA plus DB can be written as D times A plus B, which means D divides N plus M, which means this. So others are similar. And you know what's the prime number and composite number. And you know 23 is a prime number, and 34 is a composite, because it is 17 times 2, and 43 is prime, but 451 is a composite. Important thing, the first theorem, interesting theorem, starts in theorem 1.7. If N is a composite, if and only if N has a divisor, D satisfying this between 2 and square root of N. The proof was given like that. When if N is composite, then one side is simple. If N has a divisor, then N is a composite. So one side is done. And the other, if N has a divisor that's satisfying this, okay, then we divided into two cases. One is, suppose we have a the number d prime that satisfies this given condition. If d prime is less than or equal to square root of n, then it's done. If not, if d prime is bigger than square root of n, then we can find a contradiction which gives us this we have a number q that satisfies this. If you let this q as d, then that satisfies this. So we should have a divisor which satisfies this, which means n is a composite. So this is just an argument. Yeah, you can easily follow it. And this is a mathematical proof on this. But this fact is quite useful when you do code. When you do coding, you will see the use of that theorem. Okay, like this. If n is a composite, if and only if n has a divisor d such that d is a prime and also d is a square root, less than or square root of n. For example, 2 or 17 is a prime number because square root of 2 or 17 is 44 times da da da, and you can find the prime number which is less than or equal to 44, all of them, that you know. You can easily check each of these numbers cannot divide 2 or 17, which guarantees this number 2 or 17 is prime. Okay? But for number 2 or 18, then you will find some prime number that divides 2 or 18. So 2 or 18 is not a prime number. And this is the code, etc. And all those can be seen in here. Here. I will show you. Here, chapter 5. So, yeah, we go here. So divide. So here, 3 divides 21. That's right. But 6 does not divide 21. You can, if you give 7 and 4 like this, then 7 divides 21, but 4 doesn't divide it. But 3 divides 21 like this. That says we coded those. We can also check whether the given 21 is has a divisor, what kind of divisors here. The 21 has 4 divisors, which are 1, 3, 7, 21. This number has this many divisors. Those are the command to find the divisors. And we studied this in composite and this. And prime number, this is, 2 or 17 is a prime number with this algorithm, but you can use this code too. But 2 or 18 is not the prime numbers. And this is an algorithm to check whether the given integer is a prime or not. It's prime or not. And this gives 43 is a prime number. 470, but this is a composite. And this is composite, but this is still. Still, if it go big, then it can be, we have more chance to have 20. Anyway, 7. What happened? This is not working now because I have uploaded it for long. Anyway, Yeah, here I will check here. Yeah, here I will check. Yeah, these numbers are. This is composite, but this still. I want to check. Still compare. Hard to find the prime numbers. But anyway, yeah, we know there are infinite many number of prime numbers. Okay, anyway, yeah, fundamental theorem of arithmetic is also called the unique factorization theorem. Says any integers can be written as the product of powers of prime numbers like this. So any integers can be written as a product of prime numbers, and some are same, so some of them can be written as a power of prime numbers like this. This is important, so it has a name. Fundamental theorem of arithmetic. This is it. Every integer can be written as a product of prime numbers. And also there are infinite many prime numbers. Like you see here, suppose we have n prime numbers listed as P1, P2, Pn. Then if you multiply all those prime numbers and add one, then you can clearly see each of these prime numbers cannot divide this all. So we have another prime numbers. So we cannot have finitely many prime numbers because we can have more than what we already found. And also, twin primes are defined as a pair of prime which has P and P plus 2, prime number and prime number plus 2, like this, 3, 5, 5, 7, and 17, 19. These two numbers set, the pair of prime numbers are called the twin primes. And we can expect there are infinite many such prime numbers, but no one was able to prove this open problem, which is called a conjecture. So there are still many open problems in the theory of number theory, which is, has been used for cryptography. Next, common divisors. Yeah, you know what's the common divisors. Largest common divisors is GCD. It's called GCD of M and N. Suppose we have integer 30, then it has a divisors like this, and 105 has a divisors like this. Then these three, there are 4 common positive divisors among these. We call these are the common divisors. Then this 15 is the largest, the greatest common divisors among these. So we call GCD of 30 and 105 is this 15. Okay. And this is the algorithm. Yeah. This is, so suppose we have a 60, then we can have a unique factorization like this. So by the fundamental theorem of arithmetic. If we have other big numbers like this, then this is a prime factorization, unique factorization of primes for the given number. And this algorithm gives us the greatest common divisors, like this. Yeah, these are the divisors of 72, and these are the divisors of 63. And among those, and 9 is the largest common divisor. So GCD of these two numbers is 9. And yeah, we already showed it. Yeah. Only difference is alpha and betas are there, but it's just corollary of what we have shown. Next, if A divides B and B divides C, then clearly A should divide C. Easy. Yeah. A divides B means B can be written as AK, And C, B divided C means C can be written as B times L for some integers K and L. Then C can be written as A times some integers. So A divides C. The prime factorization can be written like this, and GCD can be written as this. So GCD can be written like that. Yeah. Use all the prime numbers listed, and the powers are used as a minimum of those two, AIs and BIs. So for example, 82,320 can be written here, and 95 or 796 can be written as this, the prime factors. Then GCD is what? 2 to the 2, 3 to the 1, 50 to 0, and 7 to the 4, 3, and 11 to the 0, because of minimum. Then this is the GCD, which is 4,116. For here, 30 can be written here, 24 can be written, and GCD is 2 times 3 times 1, which is 6. With this, we can code to find the GCD of given numbers like this. If you change the numbers, then we will have GCD of these two numbers, 30. Next, LCM, least common multiple. You have learned all this when you are in the middle school student. Now we are developing a code, an algorithm, to do those computations instead of us, for us. Okay? So we have to understand mathematics behind this. LCM, GCD is divisible by both 72 and 63. So LCM of these two numbers are 504. Why? Okay, here. Let's do this. 30 can be written as this. 105 can be written as this. Then 2, 3, 5, and 7 gives us 2, 10, which is the LCM of this. So from this example, we can develop some kind of algorithm to do it. So suppose we have the prime numbers like this, then we do use the maximum. We do use those prime numbers, but the powers can be used as maximum. We have 1, 2, 2, 1, 3, and 1, 5, and 1, 5, 1, 7, like this. Anyway, with those, we can code to find the prime, the LCM of given two numbers. Here, this is the theorem that we can expect. If any given two numbers, m and n, can be written as any prime factorization like this, then LCM of m and n can be similarly, but instead of minimum, that we do use a maximum of these AIs and BIs. Okay, for like this, we do use what? This should be LCM, isn't it? This should be LCM. And here, what we use is the power 2 to the 4, 3 to the 2, 5 to the 1, 7 to the 4, and 11 to the 1. So this gives us LCM of these two numbers, not GCD. Here we have 2 to the 3, 3 to the 1, 5 to the 1, 3 to 120. So we can check this LCM of this. As you see, the same numbers can be found. 1901, 5920, same. Okay. If you give a different number, then we still have the LCM of these two numbers with this code. Interesting theorem is this. if you multiply two given positive numbers, that is same as the product of GCD of Mn and LCM of Mn. Why? Why? This. Mn can be written as this. Okay? Then LCM of Mn times GCD of Mn can be written as this. We can easily check this value is same as this. So left-hand side is same as right-hand side by simple computation to show that. That's the end of section 1. And these are the code that you will use over and over again. Find the GCD, LCM, and multiply product of GCD and LCM gives us the, and what? As you see, the product of these is 4536, and GCD times LCM is same as 4,536. Same. That's as you see. You can easily check this works. If you generate the random two numbers and to check it, then you will see it works. It is equal for all. That make sense for the theorem that you see. So you should understand this, and also you should know you can prove that fact. Next, representation of integers and integer algorithms. Yeah. You have learned the decimal system and binary systems. And also there is an octal number system consists of 18 symbols, and hexadecimal number system consists of 16 symbols. So decimal number system, we did use this. 3,854 means 3 times 10 to the cube plus 8 times 10 to the 10 square plus 5 times 10 plus 4 times 1. Okay, like in here, 2 or 15 can be written as this. So 2015. So this is a decimal system examples. So in the decimal system, n can be written in this way with base 10. In binary number system, instead of 10, we do use 2 here. So in binary system, 11010 means 1 times 2 to the first, 1 times 2 to the cube, plus 0 times 2 square, plus 1 times 2, plus 0 times 1, which is 626 in the decimal system. Okay. Now we want to make a code so we can change the decimal number to binary and the binary number to the decimal numbers. Okay. In order to computer representation of those numbers. Yes. And so binary to decimal. If you have a binary number of this, then what is the value in the decimal system? So that is 45 in decimal, like this. Yeah. So from 45, if you change it to the binary, then 101101, which is this. So you can change the binary number to decimal, the decimal number to the binary, like this. Okay. This is a command. And if you have a R command or Python or other languages that you use, then you just bring it here and paste it and then run it with that particular command, then you will find the output from here. Next, converting an integer from base B to decimal. Okay, so more general. This is the pseudo code. So we show how convert the binary number 1101 to decimal. So this is a more detailed explanation. Yeah, binary number 1101 can be written as it's too long. Yeah. Just 1 times 2 to the cube plus 1 times 2 square plus 1 is the number 16. Okay, that can be found in here. 110 is 13 here. if we have this number in base 2, then the value of this is what? 1,749 in decimal. So this code gives us, whatever number we give here, and change the base to 3, then we will have this. If you change it to 5, 8, or 10, then it will be. So you can just change the base, whatever you want, and to have. So since you understand the algorithm, so you can easily make a general code that you can use not only from a base 2 to 10, and from any base B to 10. And octal number system, with the 8, the same thing. Instead of 10 or 2, we use 8 here. For hexadecimal number system, instead of 2 or 10, we use 16 here. So, but we only have numerals from 1 to 10, 1 to 9, 0 to 9. So we represent the 10 as A, 11B, 12C, 13D, 15F, the E, and 16F, like this. So BF4 in hexadecimal number system, what that means is what? It's 11 times 16 square plus F is what? 16. 16 times 16 plus 4 times 1, which gives us the value. So we, the same thing, but in that case, we should be aware. And here I can show you more details in here. Here for 16 hexadecimal numbers. Here, hexadecimal binary. Here, octa. Here, we use 10 as A, 11B, 12C, 13D, 14E, 15F, and 16 is equal to 0. Okay, so like it's a modular arithmetic like this. So this number means like the B4F in the hexadecimal number system, which means B is 11, and this is a third digit, so 16 square plus 4 times 16 plus 15, F is 15, so 15 times 1, which gives us this number in the decimal system. Understand? Miss Kim, 이해해요? 16진법? 본 적 있어요? 16진법? 없어요? 그러니까 별건 아니지. 그냥 10 대신에 16을 쓴다는 것일 뿐이죠. 근데 전에는 10진법 이하는 그냥 1부터 뭐 그 숫자까지만 쓰면 되는데 10이 넘어서면 혼돈이 되니까 그걸 A, B, C, D로 그냥 쓴 거죠. 그냥 단위를. 근데 그 A는 10이고 B는 11이고 하니까 그 차이 말고는 똑같죠. 그렇기 때문에 필요에 따라서는 코딩을 하더라도 별 차이 없이 그냥 숫자를 집어넣어주면 바꿀 수 있게 할 수 있겠죠. 다 1대1 대응을 다 시켜놓은 거니까. Okay. So, yes. Decimal to binary. These are the converting a decimal integer into base B. This is a pseudo code, and we made the real code. So, for any positive number here, base 2 is this, base 4 is that, base 87, base 100. So whatever, yeah, you can just change it, any number to any the base number systems, decimal to hexadecimal like this. So with the 16, then you list these numbers. Okay, from here, if you want to change the decimal number to hexadecimal, then divide the decimal number by 16, then you will have the remainders. And these remainders give you 4, 15, 10, 1. So when you write it, 4F A1 in 16, base 16. Got it? This decimal number can be written as a hexadecimal representation as a 4FA1 because 4, 15, 10, 1 is the digit value, each digit. Next, addition of binary numbers, binary additions. Here, 0 plus 0 is 0, and 0 plus 1 is 1. But 1.1 plus 1 is what? In base 2. The 2, there is no 2. So 2 goes to the next digit. It gives 0 to 1. So 1, 0 is the addition value of 1 and 1, binary. So if you add 1, 1, 0, 1 and 1, 1, 1 like this, then you will have 1, 0, 1, 0, 0, binary. This is the pseudo code for adding binary numbers, and this is a real code. So if you add these two, then you will have this. You will add this, then you will have, what happened? I think, yeah. Anyway, okay. You may try to code adding. Here, yeah. The thing is here. I made the addition code for only 4 same digit numbers like this. Then, yeah, it should work. But so here, if we can also make a code when that enable us to add the 2 binary numbers with a different digit number, not exactly the same. The 4-digit number and 8-digit number can be added with this by just to make some minor changes on it. And also hexadecimal addition, adding these 2 numbers can be this plus this gives us that this addition goes through there to have C7, 6, 7 additions. Repeat this square and binary principle exponent. Next exponent, computing A to the 29 using repeated squaring. Okay. 자, 여기서 잠깐. So anyway, so finding the 29th power of A, all you have to do is, if you have A to the 16, then all you have to do is just multiply A to the 13 on this. Because A to the 13 will be already found when in the process of you finding A to the 16. So if you know this will give us that, then all you have to do is just find the product of those 2 numbers. Anyway, and also here, next, here, also, yeah. Interesting thing is AB mod G is the same as A mod G times A mod G under mod G. So this is also interesting and useful fact. The proofs are written here, but as you see here, 10 mod 3 is equal to 1, 5 mod 7 is 5, and 6 mod 3 is equal to 0. Yeah, you know that, and modular arithmetic that you learned. And what about 2 of product of these 2 and mod 4D? Instead of you do multiply this to find this value, you just find the mod 4D value of 215 and mod 4D value of 217, which is 17 times and 15, yes. And then to multiply these 2 small numbers instead of this large number to have 255. Then do the modular arithmetic of 4D to give us 15. This is the same because of this fact. 그러니까 이거 큰 수를 2개를 곱해서 모두 계산을 할 필요 없이 그 주어진 숫자를 모두 계산을 먼저 해서 작게 만들어서 그 작은 숫자를 곱하면 그 같은 결과를 얻을 수 있으니까 필요에 따라서 이게 굉장히 시간을 절약하고 비용을 절약할 수 있다는 거예요. 이게 복잡해졌을 때는 훨씬 파워를 작용할 수가 있죠. 자, 마지막으로 자, 우리가 유클리디안 알고리즘까지 마치고 오늘 수업 일찍 끝내도록 합시다. 끝내고 나서 할 일도 있으니까. 자, Euclidean algorithm. We learned the theorem that allow us to compute GCD and find the prime factorization of big integers. is a challenging problem. Uh-huh. So here Euclidean algorithm gives an efficient way to compute GCD. 자, 주어진 넘버의 GCD를 찾는 이펙티브한 방법이 뭐가 있을지를 한번 생각해 봅시다. 자, 여기서 만약 A equal BQ plus R, Euclidean algorithm gives for any given number, integer, yeah, we can easily find the quotient and remainder. Then with those, yeah, we can, but important fact is GCD of AB is always same as GCD of BR, which is a much smaller numbers. If we do use this knowledge, then we can save lots of resources and time and money. Okay, for example, now this is a simple examples. And here, this is a Theorem 3.2. That's what I tell. The proof is, proof is given. That you must have read. Like you see. We wanted to show this is true. And D divides both A and B, and D divides A minus BQ, which is R. So any common divisor of A and B is a common divisor of B and R. So D divides both B and R, so D divides BQ plus R is equal to A. So any common divisor of R, B and R is a common divisor of A and B. So GCD of A, B should be same as GCD of B and R. So this fact can be used in many cases. First, Euclidean algorithm, pseudocode is given. So finding GCD of these two numbers, so instead of doing it directly, we do the Euclidean algorithm on 144, then the 62 can be used for the Euclidean algorithm, then this 20 can be done one more time with the Euclidean algorithm to have one whose remainder is 0. Then with that, this 2 is the greatest common divisor of 144 and 62. That's the algorithm. So like GCD of 144, 62 is same as GCD of 62 and 20, and which is same as GCD of 20 and 2, which is 2. Okay? And GCD. This is how it works. And this is the code to find the GCD of this number. This algorithm was used to develop this Python-based Sage code. So if you give different numbers like this, then I don't know, 1. Right. Okay. If we do use the different number here, then our GCD is 2. If we give a different number like this, then it will give. So anyway, this pseudocode was used to make a better, effective algorithm to find the GCD of given numbers, and also the mathematician at the end, Bezo, made a contribution on this part of number theory, and Bezo theorem is known as this. The GCD of AB is same as ASSA plus TB. There exists if A and B, A is missing here. A and B is in positive integers, then there exists S and T in the integer that make GCD of AB is equal to SA plus TB. For example, GCD can be written as S times 38 plus T times 52 is equal to 2. With this, we do the Euclidean algorithm to find the GCD. And with this GCD, we go to the opposite algorithm. Then we will have this the coefficient minus 8 and 11. So from this Bezos theorem, we can really find this S and T, that the existence of is guaranteed by Bezos theorem. So with this theorem, we can use the Euclidean algorithm one way and the backward to find this S and T, and that's the examples. Next part is computing an inverse modular integers, and there's an inverse of n and k if and only if GCD of ranking 1. And find the inverse of 48 mode 13 is this. This is called the inverse arithmetics. That usually be skipped. And the last part is cryptography. RSA and RSA. That is this. Here. RSA here. Here. This RSA algorithm for cryptography was developed in 1977 by Levesque and Shamir and Adelman. So RSA comes from the first capital of the three names. And this is the most popular public key crypto system, which is still used widely in our daily life. In here, this modular arithmetic that you have seen and prime factorization are used in this crypto system. And you can find those informations from this web address. I think that's the end of this chapter 5, and you have solved the self-test problems of chapter 5, and also some of you already started to solve these computer exercises. I think that's the end of chapter 5, and our midterm exam will cover the first 5 chapters up to this. So you will finish up your homework over this weekend and will be submitted next Tuesday, and then I will assign some of you to give a presentation on next Friday for those based on your PBL report. Then we will have a midterm examination in 2 weeks. Any questions?